Hello, my name is Erik Lillegard, and today we'll be talking about population models using differential equations, and in this case we'll be looking at a fish farm. We're given a model, this is model 1, representing fish population growth over time, which is governed by the differential equation y times the value 2 minus 0.1 times y. We have a graph of this function, but not as of t, as of f. And we will be able to determine the capacity once growth reaches 0, or the x-axis in our case, since we don't have that marked at 0. As you can see at the value 200, there is no more growth, which means we have reached capacity. And in this case, the capacity is 200. We will now use our little tree diagram in the bottom right to classify this differential equation. The differential equation is an ordinary differential equation, a first-order differential equation, because we are only looking at the first-order derivative, and a non-linear differential equation, because in this case, this will be to the second power, looking more like a parabola. In order to solve this differential equation, we will notice that it is separable. In this case, we will take the derivative of both sides with their respective variable. So first we need to separate this, get all the y's on the left side and all the t's on the right side. And then we will take the integral with respect to y on the left and the integral with t on the right, which will give us the general solution of 200 over e to the negative 2t minus c plus 1 is equal to y. This is our general solution, and depending on the initial condition, we can find the value for c. This is what we do so here, looking at the initial condition values of y of 0 is equal to 50, 100, 150, and 200. In this case, we will just plug in these values into our general solution with t equaling to 0 and our y equaling to our 4 values here. We have them graphed out here in the bottom left, the green referring to 50, blue referring to 100, 150 in purple, and 200 in red. As you see, for the initial conditions of 50, 100, and 150, the population is growing at a consistent rate. But then if our initial condition is 200, since that is our carrying capacity, there is no growth, so the population cannot grow any further. Now we will be looking at population growth with harvest, or a subtracting factor, a subtracting constant in this case, represented by the value negative h, which represents how many fish are taken out per year. We will simply subtract h from our previous model, which is population growth. We will then vary the initial conditions, our starting population, as well as our harvest rate, from 70 to 120 fish per year. We will then graph these differential equations and their slope fields to see whether these farms will be sufficient to suffice themselves for years to come, or if they will fail and the population will eventually fall to 0. As you see in the upward L shape highlighted in red, these are instances that the fish farm will fail. So any instance where the starting population is 42, this is where they will fail no matter what harvest rate, and no matter the initial population. If the harvest rate is 120 or higher, they will also fail. This is the MATLAB breakdown of the code. So this produces the slope fields for the population growth with harvesting rates. In green is the harvest value h, which can be changed to test different harvesting rates and strategies. And in red is the initial population value, p of 0, And together you can change each variable to find a farming model that will be successful, or more importantly, to find the combinations which produced a failure. Now looking at the data in the chart, we can say that the harvesting levels of H is equal to 70 and H is equal to 100 lead to a sustainable yield and therefore a sustainable farm. The maximum integer value of harvesting is 100. If harvesting value is greater than 100, the farm will fail. As you can see here, we test out values H is equal to 100 and H is equal to 101, and we see that at H value is equal to 100, keeping the initial condition constant at 120, the farm will be successful at H value is equal to 100, but it will not be successful at H value is equal to 101. Further analysis, as the harvest value approaches 0, more fish will be in the pond after each harvest, so your yield will be lower. This means that the growth rate will get closer to its maximum value of 200. As a farmer, you want to maximize yield while maintaining the farm's ability to replenish itself for future yields. As H approaches 100, the growth rate gets lower and lower until it reaches its minimum growth rate that would provide enough population growth in between harvests to support infinitely continuous harvests at its respected interval. So here we are testing the harvest rates, and you can see how the populations remaining after each harvest are different. So with a harvest of 20, you will have a remaining of around 80, and that will always keep your population around 180, and so on and so forth with the other values. Thank you so much. I hope you enjoyed. And if you have any questions, I'm sure I'm going to be making more videos in the future. Have a great day.